Every single day in the UK, 26,000 tons of perfectly good food is thrown away. To visualize that volume, imagine a mid-sized cargo ship packed to the brim, sinking under its own weight. This diagram tracks the sheer cost of that daily disposal. The economic drain races to over £20 billion annually, while the decomposing organic matter generates an expanding cloud that accounts for 6% of the UK's total CO2 emissions. But those macro numbers hide the reality at the very start of the supply chain. Primary growers invest months of labor and capital into a harvest, only to leave 25% of their crops in the ground. The agricultural industry calls this Class 2 surplus. It is nutritionally identical to premium lines. Major supermarket chains reject this produce strictly for failing to meet rigid cosmetic standards, meaning it is slightly undersized, oversized, or irregularly shaped. For the grower, a slightly wonky carrot breaks the contract. They are left with two options: spend fuel to plow prime nutrition back into the soil, or sell it at a severe loss to stock feed markets and biodigesters. While farmers discard crops, the public sector faces a different crisis. Schools and hospitals have struggled for decades with extreme budgetary constraints in their canteens. The UK spends £5.2 billion annually on institutional catering, yet procurement teams are constantly forced to source lower-quality ingredients just to keep their menus afloat. We have millions of tons of cheap, highly nutritious fresh produce rotting on farms, while public institutions cannot afford quality food for patients and students. In a modern tech economy, this looks like a basic routing error. The obvious assumption is that connecting these two isolated nodes is simply a software problem. This was the logic behind Ample 1.0. The goal was to build an Amazon for farmers, a digital peer-to-peer spot market where a grower could upload a photo of a surplus crop and match instantly with an institutional buyer. The platform launched, automated the invoicing, and matched buyers. Then it hit a wall. Pure digital marketplaces fail in agriculture because they treat physical supply chains like data transfers. Solving the food waste crisis requires a combination of heavy physical processing and powerful predictive intelligence working together. The baseline assumption of a peer-to-peer market: a grower logs surplus on a smartphone, and a clean digital line instantly connects them to a hospital chef. But in practice, that connection breaks immediately. The first barrier is technology reluctance. The average UK farmer is 59. Forcing complex mobile applications, live online banning sheets, and multi-step web portals onto busy agricultural workers results in zero adoption. At the other end of the line, institutional buyers face their own friction: severe labor shortages and tight meal schedules. A head chef preparing 1,000 meals a day in a hospital does not have the staff or the hours to process an unexpected ad hoc pallet of raw, unpeeled, irregular vegetables arriving at the loading dock. This brings us to the third failure point: logistics. A direct digital match means nothing if the transport geometry is broken. Moving low-value, bulky spot market vegetables requires optimal routing. Relying on ad hoc, last-mile delivery to individual schools destroys the unit economics entirely. The cost of the van burning fuel in city traffic outstrips the value of the surplus vegetables inside. Software interfaces cannot bypass the physical constraints of an aging farming workforce, understaffed hospital kitchens, and highly fragmented trucking routes. To make the surplus usable, the business model had to pivot. Ample shifted from being a passive technology platform to an active physical food processor. This led to the creation of Ample Kitchen, built through a strategic partnership with logistics operator Oakland International. Instead of routing raw vegetables directly to chefs, the surplus is directed to a centralized 12,000-square-foot facility equipped with industrial chopping, peeling, and blast refrigeration lines. This graphic demonstrates the core mechanical function. We take unpredictable, chaotic agricultural surplus in at the farm gate, process it, and output identical, standardized, ready-to-use meal components. The raw, wonky vegetables are converted directly into bulk soups, sauces, and stews. Operating at this industrial scale drops the processing cost to a benchmark of just 67 pence per kilogram. By delivering fully prepped, frozen components, the system completely removes the labor and time friction for the public sector chef. They open a box, heat the standardized unit, and serve. Bridging the gap between the field and the hospital requires heavy, capital-intensive physical infrastructure. You have to standardize the physical product before software can effectively sell it. But processing capacity introduces a new problem. A large-scale kitchen needs a reliable supply of ingredients, which requires shifting from a reactive post-harvest model to a predictive one. This is the function of FoodMatch 2.0. It acts as the intelligence engine required to scale the physical infrastructure without causing bottlenecks. Because crop yields dictate the available surplus, the system integrates external meteorological data to forecast harvest volumes weeks in advance. This automated weather API runs continuously, merging its models with low-friction manual field-level data provided by farmers via simple SMS check-ins. This chart visualizes the core function of the AI. On the left, we track highly volatile, weather-dependent crop surplus. The algorithm uses this data to dynamically align the unpredictable natural yield with the flat, rigid procurement schedules of institutional buyers on the right. Once the supply and demand are matched, the physical routing has to be optimized. This is achieved through a logistics partnership with the Logistics Institute at Hull University. The algorithm maps the transport geometry, optimizing vehicle backfilling across existing physical networks. By ensuring trucks are fully loaded in both directions, the system actively reduces Scope 3 emissions. True supply chain resilience requires AI to actively predict the physical world, aligning the volatility of nature with predictable public sector contracts. The completed ecosystem operates in 3 stages. Low-friction aggregation at the farm gate feeds heavy physical processing infrastructure, all guided by an AI demand matching engine. Together, these mechanisms formalize a new procurement path that actually removes emissions from the atmosphere. Look at the standard wholesale pipeline on the left, heavy with transport and disposal emissions. Contrast that with the circular model on the right. Rescuing food that would otherwise rot and release methane drops the net carbon impact below zero. For the primary grower, the economic impact is immediate. Crops that were previously guaranteed losses are monetized, injecting direct revenue back into rural farming communities. For the platform, operating this closed loop presents a massive commercial opportunity, projecting target gross margins of 87%. This infrastructure is built precisely for the upcoming UK government mandate, which requires 50% of all public sector food to be sourced from domestic small and medium enterprises by 2030. Ample's target is to process and deliver 150,000 nutritious meals per week, capturing a critical slice of the £5.2 billion public sector market. Software alone cannot fix a broken physical supply chain. Getting food from soil to a hospital plate requires merging digital intelligence with heavy physical infrastructure.